In this video, we're going to be talking about how do we find the area of a shaded region where there are multiple intersections. So occasionally when we're finding area between two curves, there are multiple points of intersection, and that really means that we need to set up multiple integrals in order to calculate the area. On these questions, the first thing we're going to have to do is find the points of intersection. Then after that, we can set up the integrals and solve to calculate the area. So let's take a look at question 1 here. So we can take a look at this graph of sine x and cosine x, and we can see that there's really two shaded regions here. And what we want to do is find the total area of those shaded regions. So what we're going to first do is, I'm going to zoom in on the graph a bit, is we're going to identify these points of intersection. And in particular, we need the x values here. So we could either read the graph and determine those values, or we could set these functions equal to each other, solve algebraically, or solve on our calculator, putting them in y equals. But I can see that this first intersection is at -3 pi over 4. I can see that this top intersection over here is at pi over 4, and this last one over here is at 5 pi over 4. So if I zoom out a bit, that's really what part A is asking us. So we want to list the x values of the points of intersection. So that's -3 pi over 4, pi over 4, and 5 pi over 4. Now, generally on questions, they're not going to ask you to find those points of intersection. You're just going to have to know to do that in order to set up the integrals. And there's also a suggestion here to list them in order from least to greatest. That's because when we go to part B and we are setting up our integrals, we can see that this first shaded region, so everything in here basically that I'm coloring in, we can see that that goes from -3 pi over 4 to pi over 4, whereas the other shaded region is going from pi over 4 to 5 pi over 4. So those are going to be the two bounds of the integrals that I set up. So the first is going to be from -3 pi over 4 to pi over 4. And we're going to look at upper function minus lower function. So when I actually scroll back over to the graph here, if it's helpful, we could highlight these functions. So let's say I take a pink highlighter here and I'm going to highlight the sine curve. So the sine curve, sine of 0 is 0. So I know that this is our sine curve. And let's say I go in with another highlighter here and I'm going to highlight cosine in blue. If we look at that first region, cosine is the higher function, the upper function, sine is the lower, and then it reverses. In that second shaded region, sine function is on top, cosine's on the bottom. So I'm going to have to take that into account when I set up my integrals. So this first one is going to be cosine x minus sine x dx, and I'm basically going to add that to the integral from pi over 4 to 5 pi over 4 sine x minus cosine x dx. For part C, we're asked to calculate the area between the two curves. So if you take a look on the right of my screen here, I have already put this in my calculator, and we're going to do 3 decimal places. So the area is 5.656. You, of course, could integrate this by hand as well and plug in the bounds and evaluate using the fundamental theorem of calculus. The other thing to note on this problem is you might know a lot about the sine and cosine functions and realize that the area of the two shaded regions is equal to one another. So if that's the case, what you could also do on this problem is find the area of one shaded region. So perhaps the one from -3 pi over 4 to pi over 4, and then just double that area. And you can see that being verified on my calculator screen on the right-hand side. Okay, for number 2, we are going to find the area of the shaded region that is bounded by the graphs f of x equals 2x cubed minus 3x squared minus x minus 3, and also g of x equals x squared minus 4. So the first thing that I did, you can see on the right of my screen that I've already done this, is I took the first function and put it in y1, and I took the second function and put it in y2. The reason I'm doing that is because I need to find the points of intersection of this graph. If we think about question 1, that was the first thing that we did. And if I look over here, I can see that there are going to be 3 points of intersection, and they look like from the graph that these are going to be decimal values. So I can't just read the values from the graph like number 1. I have to use my calculator to help me find the intersection. So now that I'm looking at the graph, I'm going to do second trace, and then choice 5 to find points of intersection. If you're using an actual calculator instead of this app on the iPad, it might look a little bit different. You might have little cursors on yours. But basically, you're going to pick a left bound and a right bound. And I can see here that the intersection is occurring at x equals negative 0.55139. So I'm going to list that first intersection over here. And then basically what I'm going to do is I'm going to repeat that process. So you can pause the video if you need to. And I'm going to repeat that process for the other two intersections. So I have already done that prior to making this video, so I am going to just write them here for you. But again, you can pause the video to find and verify them yourself. Yours might come out slightly different in terms of the decimals all the way at the end. That's just a matter of the different calculators. All right, so now that I have this, I have to determine, can I write one integral to represent the shaded area, or do I have to write multiple like the previous problem? So if I take a look at this here, let's trace the curves in colors again. So let's say I take the parabola and I make it blue, and I take the cubic function and I make it pink. When I look at this first shaded region here, the pink function is on top, blue is on the bottom. But for the second shaded region, it flips, right? So in this case, I know I have to set up two integrals here. So what I'm going to do is I'm going to set up an integral from the first 2 points of intersection. You'll notice that I found them in order from least to greatest. So that's going to be the integral from, let's see, we have negative 0.55139 all the way to 0.4268173. And for that, I have my upper function, so f of x minus the lower function g of x dx. And of course, you could substitute in that actual function. So instead of g of x, for instance, you could write x squared minus 4. And then I'm going to find the area of the second shaded region. Okay, I'm going to use that point in common, so the 0.4268173 as the lower bound. And then the 2.12 and so on for the upper bound. And now this time it's g of x minus f of x dx. So I'm going to put this in my calculator in order to evaluate here, and I have already done that. So you could verify this in your calculator as well, but this is going to come out to 3.662 as the area of that shaded region. Okay, for this last question, number 3 here, we are going to find the area of the shaded region bounded by 4 cosine x and x plus 2. If we take a look at our graph here and I zoom in, I can see that there are 3 points of intersection that I need to find, and I've already gone ahead and found them in the calculator. I also notice that if I trace over my curves or just look at each of the shaded regions, I can tell that basically for the first section, the line is on top and the cosine curve is on the bottom, and then it flips. So over here, I have already found those points of intersection. If you need to pause the video to find them on your calculator, you can do so. Okay, so now let's write our integrals and then we'll evaluate to calculate this area. So the first integral is going to go from negative 4.14 so on to negative 1.42. You can see in that section either on my calculator screen here, or if I slide back over here, that the line is the upper function here. So we're going to have the integral from negative 4.14608 to negative 1.42707, and it's going to be x plus 2 minus 4 cosine x dx. And then over here, we're going to have the integral from negative 1.42707, and that's going to go to 0.79659. And now it's reversed, so it's going to be 4 cosine x minus x plus 2. We have to distribute that negative out, dx. Okay, I'm going to use my calculator to evaluate this. So if we take a look at my screen over here on the right, I have already plugged these integrals in. I've also added them together, and we're going to have our answer to 3 decimal places, which is 8.267.